spin-off talk. You know that the idea of talks is that every last Thursday of the month, we have a NanoSpin-off company, and they tell us about their experience. Today we have a GRAPHENEA, which is, okay, NanoSpin-off, but it's quite a big company now, I would say. They start at the beginning of the graphene, and they have a lot of developments, and I think there will be a very interesting presentation. We are very lucky because we have here Amaya Frutuza, and she is the scientific chief officer of this GRAPHENEA. So we don't have a commercial here. We have a person that knows what she's doing. So she has a very brilliant CV. She received her PhD in polymer chemistry. She's a chemist, and she received her PhD in polymer chemistry in UK in University of Strathclyde in Glasgow in 2002. Then she did a postdoctoral stay and working in molecular imprinted polymers. So she was always in the field of polymers. Then she moved to the pharmaceutical industry. And after that, she changed over and incorporate GRAPHENEA in 2010, when she became scientific director of GRAPHENEA. And since then, she has been involved in many different EU projects. So she has been in 26 EU projects, which is saying this in 13 years. It's a lot. And I don't know how she did. Of course, she has during this time a lot of publications, including publications in Nature and Science. And she is also part of the European initiative of Graphene Flagship. She will tell us a little bit about this, which is very important. So it's one of the leaders, scientific leaders in graphene. So we are happy to have him here. The floor is yours, Amaya. You have here students, you have here people working in carbon from our Institute of Carbon Chemistry. So the floor is yours. You can start. Thank you.
Great. Thank you. Well, good afternoon, everybody. I'm sorry I cannot be there. It would have been great, but yeah, due to other commitments, unfortunately, it has to be remotely. Thank you, Reyes, for the kind introduction and for the invitation. I hope you find the talk interesting, and yeah, there will be some time for questions. So I'm going to talk about graphene from synthesis to applications. As Reyes said, I mean, I was the first person they hired in GRAPHENEA in 2010. But in these 14 years, a lot of things have happened. I mean, at the end, graphene is, or it was at least, a hot topic. That's why we have been actively involved in many different European projects. And yeah, I think graphene has evolved a lot in these 14 years. So before I go to the main part of my talk, I wanted to a bit introduce graphene, right? So I guess you all know, and since the audience is an expert in carbon materials, I wanted to tell you about the beauty of graphene, and the extraordinary properties are due to its electronic band structure. And this band structure was theoretically predicted many years ago. So in 1947, Wallace published a paper talking about graphene's unique properties and electronic band structure. So this band structure makes the charge carriers in graphene behave as if they had zero effective mass. What does this mean? That they move very fast. So electrons and holes in graphene move very fast, and they give graphene these extraordinary electronic properties. So apart from the electronic properties, we also have other very interesting properties. It was the first atomically thin material to be discovered. So it has the thickness of 0.345 nanometers, really nothing, but it can be very large on the XY plane, as you will see. It is transparent. It only absorbs 2.3% of visible light. It is also an excellent thermal conductor. It was found to be 300 times stronger than steel, but of course, comparing to a steel of the same thickness, so very, very thin. And it is, of course, fully flexible, and also it can be stretchable. Okay, because of all these properties, it is expected that graphene will impact in many different markets, and we will have different products based on graphene. But today I'm going to focus to sensors, so that will be the main part of my talk, and focusing on electronic applications such as sensors, let's say. A bit on the discovery of graphene, just briefly. I mean, even the discovery was quite a nice story, right? It was isolated in 2004 with those three components. So Scotch tape, graphite, here is in the form of a powder, and this is a silicon wafer. So with only these three elements and an optical microscope, they could see graphene for the first time. And 6 years later, after the discovery, well, they awarded the Nobel Prize to the two scientists involved that now, of course, are very famous. And this is how it works, or how it worked, how they found the graphene. So here you can see this is a monolayer graphene flake, and you can see it's pretty large. I mean, typically you get a mixture of different layers, bilayer, trilayer, and the single layer is this one. Right, so a very small piece, and you use a Scotch tape. That's how it was developed. Of course, this is how it was discovered, but this is not how we make it nowadays. And of course, as you can see, this maybe is not so scalable for the industry, right? So I will also show you how we make it in a more scalable manner in industry. A bit on GRAPHENEA. We are located in San Sebastián, in the north of Spain. We produce and sell different graphene materials. On one side, we have a business unit that deals with graphene oxide and its derivatives. And on the other hand, we have CVD graphene that I will explain you how we make it. And this is the graphene that is suitable for electronic applications. We are around 40 people, and I already said we were founded in 2010. We also have a sales office in the US, but our main facilities, R&D, production, is all in San Sebastián. We do the processing of the wafers in a technology park, and then device fabrication in a nanotechnology research center in PIC NanoUne, or CIC and NanoUne. We supply to more than 60 countries. I think the last I heard, we had sold graphene to more than 800 customers distributed worldwide. So, and then the numbers keep increasing, yeah. And the circle, the bigger, the more we sell in that country or area, let's say. Okay, so a bit on GRAPHENEA semiconductor. CVD graphene is produced in a clean room. You know, particles are an issue for when you are making small devices, also contamination. So you need to keep that to the minimum. And I said we also produce devices or chips. And our idea is we will be moving. So this building is currently being built. It's on the same street, so a bit farther down the road. So there, our plan is to have a manufacturing facility for chips, for graphene chips on 200 millimeters. So yeah, that's where we are aiming, and we will hopefully move there in a couple of years' time. Yeah. Okay, so now I move to the main part of the talk. So this is the outline. We'll talk a bit about the fabrication. After that, of course, I want to tell you why graphene is great in sensors, especially from the business perspective, not only from the material perspective. Or scientific interest, but from the business perspective. And then I will show you some results that we have obtained in different projects on biosensors for detecting SARS-CoV-2, also on gas sensors and ion sensors. And I will finish off with some conclusions. Okay, So what are the challenges on the development of CVD graphene? And these are just some broad challenges, so you keep in mind, right? So we want to produce CVD graphene at large wafer scales, ideally 200 or even 300. As you know, most electronic components are produced at that wafer scale. So in order to go towards industry, towards product, you need to produce it at a relevant wafer scale. You want the process to be reproducible, all the graphene homogeneous, wafer to wafer reproducibility, and so on. And then one big challenge is how we integrate graphene into the final product. Is it going at the top? Is it going in the middle? Is it going at the bottom? Anyway, we need to develop all that. And last but not least, quality control is also critical, and we need to do it at different steps of the manufacturing process. Okay, so in order to move from the lab to the market, what are the steps for CVD graphene? So we need to grow it, then we need to transfer it, and then we do the device process. And I will explain how we do each one of them. So for the growth, we use a CVD reactor, chemical vapor deposition reactor. It is a thermal process. This means only heating is used. Initially, there were some papers reporting plasma, the use of plasma, but plasma is a bit, I mean, it induces defects in graphene. So only with thermal, only with heating, you can get quite good quality graphene. We need a catalyst, so we use copper foil as the catalyst. So this is an actual image of the holder that we have in the reactor. So this is the system that we have in our clean room, and we can grow 200 by 200 millimeter copper. Well, graphene on copper, sorry. So we put this, we can grow 2 foils at the same time. So we introduce these 2 copper foils. We go to 1000 degrees, introduce methane, and we form this monolayer of graphene that is 0.345 nanometers in thickness, and is fully continuous. It is not single crystal because typically you have different nucleation spots, and the grains grow and finally merge to form these large films. You can also use other setups, other CVD type of reactors. Another option could be a tube furnace. This is a hot wall system. You heat the walls, basically. In this case, the walls are cold, it's the cold wall systems, and we use electrodes for heating the foil. There are also roll-to-roll systems. If you want to go into continuous, then you do it in the form of an open system, like roll, and you produce a lot of graphene. And then the final option would be to use an MO CVD reactor, a metal oxide CVD type of reactor. So there are different options to grow graphene. Okay, we have experienced an evolution on the size of samples that we were growing. Of course, I mean, in these almost 14 years, gives you time to develop the product, the growth, the transfer, and so on. So you can see here how, I mean, we started with really small samples, then we moved to 4 inches, which is like 100 millimeters, then to 150 millimeters, and now we are at 200, which is the relevant scale for many industrial applications in the semiconductor industry. What are the key aspects to take into account for the graphene growth? Well, as I said, you want the whole film to be the same, so you want homogeneity, you want all the runs to be the same. Challenges that we face when growing on foils is sometimes at the nucleation point, we have a multi-layer forming. So you want to minimize that. You want the foil to be as flat as possible. The rougher it is, the more defects you can induce there. Another factor is the orientation of the copper. Typically, we use polycrystalline copper foils, but we also do research into single crystal copper catalyst, but not in the form of foils. But okay, I'm not gonna complicate today the talk, and let's stick to the foil. Okay, for the quality control, I mean, we need to use a plethora of methods, but Raman spectroscopy, as you know, is very relevant for carbon materials, and we do it routinely. We do it on 200 millimeters. We, as you can see here, we do different areas, typically top, bottom, and in the center, different areas. We get statistics to see that the growth is under control, and we are getting always the same. Okay, and for the transfer, in a similar manner, we have experienced an evolution there. So from coupon level, like really small samples, to 4-inch wafers, 6. Now this is, I mean, here you can only see the wafer, basically, because I mentioned graphene is transparent. But this is an 8-inch silicon wafer fully covered with graphene. In this case, here we have a 12-inch or 300 millimeter wafer where we transferred a 200 millimeter graphene on it. I mean, you can maybe see it here at the edge of the graphene film. So it's a 200 millimeter. Hopefully in the future, when we move to 300 millimeters, we will be able to cover all that. Some of the key aspects to take into account in this transfer process, well, you want, first, if the growth is good, you want the transfer to be good and to have a low percentage of defects. You want also the graphene surface to be very clean. Also, the interface between the graphene and the substrate has to be very clean. If we want this wafer to be processed in existing fabs or semiconductor industry fabrication plants, we need to ensure also the metal contamination is below a certain level. And those requirements are quite strict. So there is a lot of work also in decreasing metal contamination on the graphene film, taking into account, of course, that we use copper. It is a metal for growing it. Yeah. So anyway, but we have demonstrated that by applying specific cleanings, you can decrease the contamination of graphene from those. It's free of metal contamination. Again, homogeneity, reproducibility are very important, but I wanted to mention here addition. So the graphene on these substrates is just touching. It is they are by van der Waals interactions. So these interactions are quite weak. So what can happen is that graphene can detach from that substrate. So you need to optimize the transfer process in order to also improve this addition and maintain the full film on the substrate. Yeah, and I will show you an image of what happens when you have bad addition. Basically, it's not good, but I will show you, I think it's the next slide after this. In principle, you can transfer graphene onto any substrate. So different substrates, it can be a flat substrate, only silicon with silicon dioxide. It can have metal contacts at the bottom, a waveguide containing wafers. I mean, these are some images of this substrate, actually. We could also suspend graphene over cavities. So yeah, so this transfer process enables a lot of, it has quite a lot of versatility. Okay, and here is the image of what happens here. So you can see there are patches where there is no graphene. So addition is a big challenge, and optimization of addition, takes a lot of our time, basically. This work was carried out in the framework of the graphene flagship with IMEC. We have worked a lot with them. I mean, we have published some papers with them, but today, I mean, this is for photonic applications. So since I'm going to cover sensors, I'm not going to give much details, but feel free to ask also if you want more information on that. Okay, so now for the biosensors and gas sensors and ion sensors, we need transistors, right, that can work in liquid environments. So we have also started fabricating and selling graphene chips. So this is an image of a graphene chip. This is 1 by 1 centimeter, so relatively large. We have the contacts, the metal contacts, well, apart from this, the on-chip gate, are fully encapsulated in order to be able to deal with liquids. Because for a biosensor, you want to detect a biomarker in a liquid sample. And basically, we have 2 sets of transistors. So here there are 6 graphene transistors, and at the bottom another 6. We see a zoom-in area of this. You see these squares are the graphene channels where we would put the biological sample, let's say. We have also made a smaller chip. So this is only 4 by 4 millimeters. Fully packaged already, and with you can get a GRAPHENEA card in order to read all those devices and measure all the functionalizations and the biorecognition events. Yeah, we fabricate the devices at 6 inches, so 150 millimeters, and of course we do quality control. We measure the optically but also electrically, and we obtain this type of heat maps for qualifying the wafers and also identifying individual chips that are not good. We also offer a graphene foundry service now, on this sense. Okay, so moving a bit further, I wanted to tell you about graphene's unique selling proposition in sensors. So the main point is that graphene has shown a great sensitivity to detect certain biomarkers. And because it's all surface, it can detect very small changes because of that. The integration into CMOS technology, or let's say CMOS is semiconductor industry, CMOS wafer is a semiconductor industry wafer that has all the electronics. It means, a complementary metal oxide semiconductor. So you would have all the electronics there, and we can just put graphene on top by doing the transfer process. So the integration is pretty straightforward. It's not expensive. So this is another barrier that we can overcome using graphene. So this is also an interesting, unique selling proposition. All the processes that we use for fabricating graphene are semiconductor industry compatible. So we use tools that are available in the industry for transferring graphene, for bonding it, for etching, and so on. And the final point for sensors is that, of course, graphene, I said, has a great sensitivity, but it's not specific. So it changes any change on the surface, happening on its surface. So in order to detect something that you want, like a certain biomarker or the SARS-CoV-2 virus, you need to make it specific. And how we do that? By functionalizing the graphene. And the good point is that the functionalization strategies are really versatile on graphene. And I will show you some examples there. So you functionalize with metal oxides, you can make graphene sensitive to a certain sensor. You put ionophores, it can detect potassium or sodium. And then if we, of course, use bioreceptors like DNA or proteins or antibodies, then we have a very specific biosensor based on graphene. And for graphene field effect transistor biosensors, I said it has been demonstrated there are many publications out there where they have got great sensitivity. And I'm going to show you one example that of recent work that we published last year. The TRL means technological readiness level. And this is, so TRL1 is when it's only the idea, TRL2 is you can maybe start doing some experiments, and TRL9 is when it's in the product. So the TRL level of different biosensors depends, of course, on the functionalization strategy and the biomarker that you want to detect. One maybe, let's say, not so positive side, and because it's quite a new field of research, this graphene field effect transistors for biosensing application, there is limited work published so far using complex biological samples. But I have to say, in the last 1 or 2 years, more work is coming out. So it seems we are moving in the right direction. And the last point is that this platform, so GRAPHENEA, if it is for biosensing for point-of-care applications, has a great potential, and you will see why I say that. Okay, so if we take a conventional transistor where we have a source-drain metal contacts, we typically use a bucket, and this is typically doped silicon. Okay, but what happens in a graphene FET biosensor? So we move from measurements in air to measurements in liquid, right? So we move from a bucket to an electrolyte gate because we want to detect biomarkers that are in solution, right? And when we have a solution containing ions, graphene is capacitively coupled to these ions, forming an electric double layer. So this electric double layer is like the oxide from this bucket configuration, right? And this means that when we have these ions and the graphene is really, really close to the sensing event. And that's why we can make very sensitive biosensors. If we check a bit the equations behind these transistors, here the drain source current, we want to maximize that. How can we maximize it? So by making the device smaller, this is really possible with graphene. It's very easy. You can make the device as small as you want. Of course, it has to be large enough to be able to put the drop and to wet the graphene. But in principle, this can be, you could use micro droplets and make a very small device. So that way we could enhance the performance of the transistor. The second point is the mobility. So in the case of graphene, this mobility is very high. And another important parameter is the interfacial capacitance. And this is also high in the case of graphene in comparison to, for example, silicon, as I will show you a table on the next slide. And why is high the interfacial capacitance of graphene? Well, because we have also the quantum capacitance contributing to this interfacial capacitance, not only the capacitance of the double layer. And another interesting point is that the operation voltage of this transistor is very low. So the source drain current can be from 10 to 100 millivolts. So this means it's very efficient, it has a low power consumption, and it could be portable, right? So that's what we want for point-of-care applications, to be able to apply them at home or in hospitals or, yeah, at point of care, basically, yeah. Okay, so if we check, if we compare graphene to other materials on these two parameters I just mentioned, so mobility and interfacial capacitance, you can see how, well, this is, I mean, I got this from these two papers, and these are already quite old, so the mobility values of graphene have improved quite a lot. But even here, I mean, if we take CVD graphene, I mean, you can see that the value is much better than to the other materials. And in the case of the interfacial capacitance, is also much higher than silicon. So this is translated in these transistors to a high transconductance, and this is what you need to have a high sensitivity, basically. And for more information, you can check those two papers, yeah. Okay, so what is the operation principle of this transistor? So what changes the electrical conductivity of graphene? So doping can change the electrical conductivity of graphene. Also conformational changes on bioreceptors, like the case of aptamers, and I will show you just now. And also a change in the carrier mobility can change the electrical conductivity of graphene. So if we check these transfer curves, so how the source brain current changes with the applied gate, we get this type of curve. And basically what we are following is the shift of the Dirac point or charge neutrality point when you expose it to a biomolecule, let's say. So for example, if we put a molecule on top of graphene that donates electrons to the graphene, then it n-dopes the graphene and we see a shift to the left. If on the contrary, we put a molecule that withdraws electrons from the graphene, then we have p-doping and we see a shift to the right. And that's the transduction mechanism of this transistor. In the case of aptamers, they have a conformational change when we have the target of interest, and this induces an electrical conductivity change on the graphene channel. Okay, how does it work? So I said we have to make it specific by functionalizing it. There is a lot of work published on the functionalization of graphene. Initially, a lot of focus was on covalent functionalization, but now most papers have moved to the non-covalent. And why? Because the covalent functionalization means you are disrupting the graphene honeycomb lattice and you are decreasing the mobility. And we said the mobility is a very important parameter for having the sensitivity there, right? So that's the reason why now most researchers have moved to the non-covalent functionalization. So the non-covalent functionalization typically has 2 steps. So first, we put a linker on the graphene. I mean, I'm showing you an example here of p-base because I will show some results on that later on. So we have pyridine molecules, pyridine-based molecules that are non-covalently interacting, so by pi bonding to the graphene lattice. So that's why we call this non-covalent functionalization. And then the other part of the linker is the one that we attach covalently to the bioreceptor. And in this case, this is an antibody. So linker molecules, different options. You can use p-base, TCPP, PMAL, any pyridine derivative, basically, that you can attach covalently to the bioreceptor. And as bioreceptors, many works have been published using antibodies, aptamers, enzymes, proteins, DNA, and so on. And then once you have functionalized it, you are ready to detect the biomarker of interest or the target biomarker. And in this case, I've put an image of SARS-CoV-2 because I will show you some results on that. So in this case, the antibody is specific to the SARS-CoV-2. So when we put a sample and expose this biosensor to SARS-CoV-2, we have a transduction in the signal, a change of the Dirac point, and that's how we detect it. One challenge on these biosensors, I mean, I wanted to tell you because not everything is great, and we have certain challenges. One challenge is the low concentration of samples, right? So the biomarker of interest is present typically in real biological samples at very low concentrations. Well, this is a challenge, but it can be an opportunity because graphene really can detect the presence of molecules at very low concentrations, and I'm going to show you results on that. The second point, and this is maybe a larger challenge that maybe is not so much an opportunity. Okay, there are ways of overcoming it, but one fact is that complex biological fluids contain a lot of ions in solution, and these ions can screen the effect that we are interested in detecting. And this means that the debye length can be shortened in biological fluids. And that means we could be outside of the window that we can detect that biorecognition event. So how can we overcome this challenge? So one way would be to use smaller bioreceptors. So typically when you use antibodies, antibodies are really, really large. So by replacing an antibody by an aptamer, we can make it smaller and be within this debye length. And another way of increasing this debye length is by adding, for example, polyethylene glycol in order to stop the screening of these charges. So there are ways of overcoming, but it's something to keep in mind, especially for biosensors. I'm not gonna maybe give too many details on here. So we are using these 1 by 1 centimeter chips for the results I will show you. So basically, when we check them, we check the transfer characteristics only of the chips in PBS. We see that most of the transistors are behaving pretty well, and the deduct point is pretty much the same for all of them. So we are ready to functionalize them. So before I show you the results, I wanted to tell you a bit about this point-of-care diagnostics market before and after SARS-CoV-2. So when COVID-19 appeared, this market experienced quite a large increase. And it is expected that, unfortunately, other viruses will also appear. And of course, we want better diagnostics for cancer and so on. So it is a market that it is growing constantly, and it will experience growth. So it's a very interesting market from the business perspective. Okay, so now I go to the results. So this work we published in collaboration with TIC Biogune, that they are also in San Sebastian. So everything is close by. And we use these chips that I showed you before, an S20 chip. And basically we used P-base as the linker. And we attached to P-base ACE2, which is the human membrane protein involved in the internalization of SARS-CoV-2 type of viruses, right? So this is the bioreceptor, the ACE2 that we attach to the P-base. And then once the system is exposed to the spike protein of the SARS-CoV-2, because we couldn't handle live viruses, we selected the spike protein, which is the mechanism that these human membrane proteins attach to SARS-CoV-2, then we have the biosensor working. Okay, so for this debye length that I talked before, in order to determine what would be the functionalization length, we used AFM, we opened the window, and we determined that the thickness of the functionalization layer was 3.3 nanometers. So by using some mathematical equations, we back calculated let's say the ionic force of the electrolyte of the PBAs, let's say the phosphate buffer that would be ideal to use in order to detect our biorecognition event. And this was around 8 millimolar. So we stick to that concentration, and we added the spike protein to that solution in order to sense this molecule. Yeah. So these are the results. So I told you we could get very low levels of detection. So by following the shift of the charge neutrality point, we got a linear dependence, and the low limit of detection was 3 attomolar. So 3 attomolar is pretty impressive detection limit for a biosensor. Of course, we didn't use complex samples. Our idea is hopefully to test saliva, so real samples, but this was not done with real samples. The level of detection, of course, is expected to decrease a bit in real samples, but nevertheless, I mean, the starting point is pretty attractive, and that's why we think graphene has a great potential in biosensors. Yeah. Okay, so just to sum up this work, and of course there are still challenges to be solved, how we anchor the bioreceptor, how we overcome the divalent, the use of complex samples. As I said, this needs further development. Another point that I show you all the time, I was talking about the chip, right? So 1 by 1 centimeters or 4 by 4 millimeters. Because in order to go to products, we need to move to full wafer scale for the functionalization, not only for graphene growth, transfer, device fabrication, also for the functionalization. So all the steps will have to be scaled to full wafer scale. Some bioreceptors, I mentioned aptamers. Other aptamers are very interesting, but they are also in development phase. So yeah, if you take an aptamer, it will need a longer time to develop into a product. To ensure commercial success, it's key to select the right biomarker and the targeted market. Last year, we did a road mapping exercise, and graphene biosensors appeared in the roadmap, so they are really a potential product. The time to market was medium to long term, 5 to 8 years. I think depending on the functionalization, if it's more simple, less steps, then of course the time to market can be decreased. And the reality is that we expect in the next years, a few years, to see graphene biosensors in the market. The work in research related to FET biosensors has experienced a huge increase over the last years, judging by the number of publications. And the last point is that there are a number of startups that have been created to exploit graphene FET in biosensing applications. So this tells you that the ecosystem is being built, is being developed, and we hope to see products in the market soon. Yeah. Okay, so for the gas sensors, I only have this slide. So the functionalization here is more simple. We worked in collaboration with the University of Tartu and Infineon in the framework of the graphene flagship. They used pulsed laser deposition to deposit metal oxides on graphene to make them selective to NO2 or ozone. And then by applying machine learning on the response patterns, we could even predict the concentration of the individual gases. So it also shows quite great potential for gas sensors. A final example on graphene for ion-sensitive field effect transistors. Here we have a long-standing collaboration with McGill University in Canada. And here they demonstrated how we can measure in real time with high resolution simultaneously many multiple ionic species in an aquarium containing duckweed. And how we did that? Okay, so this work was done at wafer scale at 4 inches, 100 millimeters. We transferred graphene onto pyrylene C, coated silicon wafer, then deposit metal contacts, then split the individual devices. We put different ionophore mixtures that were selective for different ions, so potassium, sodium, and so on. And that's how we got a simultaneous measurement of the different ions. And yeah, so anyway, for more information, you can check the paper, but it's also a very interesting and relevant application because the monitoring of ions at low concentration is very relevant for many industries. Yeah. Okay, and yeah, I see my time is up almost, so getting there. I wanted to tell you maybe the overall graphene market potential. I was checking different market studies. It's not easy to all the time, to let's say analyze all these market studies. They have quite disparate numbers depending on what company publishes them. But I liked this one because it gives also a split related to applications. So the ones I mentioned, all the sensors would go in this electronics segment, but of course, like graphene oxide, graphene flakes would be more relevant for energy or aerospace and defense and automotive type of applications. And the graphene market was valued around $300 million in 2022. But the interesting is that most market studies are predicting quite a large growth. So this market study I selected was predicting that would go up to $3 billion by $3 billion US dollars by 2030. So I think the graphene market in different applications is moving in the right direction. We already have a market there. Okay, it's not so large, the global market, but yeah, the good thing is that it's expected to grow, and we see different potential applications getting there very soon. And the last but not least is that patience is the key. So if we check history and different advanced material examples, we see that they have taken many years to reach the market. We take the silicon industry. Now silicon transistors are everywhere, mobile phones, computers, all sorts of sensors. But I mean, they have taken a lot of time, many years, a lot of investment to be where they are. And yeah, the first transistor was developed in 1947, long time ago, and it was not even based on silicon, it was based on germanium. So you can see how life can change things, right? And development, manufacturing, maturity can change a lot of things. And it takes a lot of time, yeah. We take the aerospace industry, the time to market is even larger, yeah. They don't implement new materials very fast, yeah. Even yeah. So anyway, a lot of examples out there, yeah. And just to finish off, I hope I stick to my time. I hope I show you that graphene has a very strong, unique selling proposition in biosensors, especially for point-of-care diagnostics. The time to market, depending on the biomarker of interest, will vary, and the functionalization strategy. But we expect that in the next 3 years, there would be graphene biosensors in the market. The graphene integration maturity has increased a lot in the last 5 years. So we are getting there, and we are progressing in the right direction. There is an ecosystem of startups distributed worldwide, not only on biosensors, but also for photonics, for optoelectronic applications. And they are there to commercialize these technologies. So they only need a final push to go to the market. And yeah, maybe as a result of the graphene flagship, this was a 10-year project that the Commission invested, that finished just last year. 16 spin-off companies were created with the aim of introducing graphene to the market. Yeah. So yeah, so interesting days and years will come, hopefully. Yeah, and I thank you all and my team, and yeah, Arantxa and Alba, that did a lot of work in the flagship and in the experimental pilot line, and our collaborators, and yeah, you for your attention.
Thank you very much, Maya. So I really focused. Okay, so thank you. Very interesting, no? And amazing, no? How you increase from the 1 centimeter going to 20 centimeter. Huh? That's a lot. So let's see. We have some. Do we have questions in the no? In the audience here in the audience, do we have any questions? Shy people. I may start.
Okay.
Okay. So I have several questions. One is about you talk about one of your products, which is the graphene grown by CBD, okay, and for the sensors and so on. But you know, I am a customer of other of your products, which is the graphene oxide that you see also, that may be used for many other different applications than just the specific of the sensor. So how do you see the incorporation of graphene, starting from this graphene oxide in different materials? What is the time to market for that?
So that is more mature. So the CVD graphene, the technological barrier is larger because the semiconductor industry is, let's say, investment hungry, I would say. So everything a tool costs much more. The graphenoside is a bit more mature. Yeah, that would be for another talk. It is closer to the market already. So we have industrial customers buying decent volumes. Now we ship even, we have made a new brand that will be commercializing industrial additives based on graphene oxide that is called Kiboro. So yeah, it's more mature. The technological barrier is lower, but yeah, it will be in the market soon in different applications. Yeah, much faster than the other one.
Much faster than the other one. Maybe
Yeah.
this is the key, because you mentioned that there is a long time to market, that we have to be patient. Science is the mother of patience. And so what is the keys for a company to stand up there with a lot of investment that you need to do, and at the same time not having nothing for selling? So is deep diversification of your products that was the key of GRAPHENEA, or what is your opinion?
That's a good question. So we started quite early selling materials for research. So we were aware that the research market would be small. I think it is small, but it is a market. And so that was a way of minimizing risk. So we have some sales from research materials that pay part of our bills, some salaries. Then another strategy that we have followed, and it was also necessary to develop the materials, not only graphene oxide, also CVD graphene, was the involvement in European projects, and the flagship has been very critical there. So the flagship has enabled us to collaborate with top research centers like IMEC, different companies, startup companies. So it has put all the community together, focused in certain objectives. And yeah, it was a real push. Yeah, I have to say, I think only 10% of startups passed through the 5-year anniversary. So yeah.
Yeah, that's
not easy, the business world.
not easy, not easy. Because we think as a scientist, and we think in a wonderful life. The other day I have presentations of the students of the Erasmus Mundus Master, and they were thinking that it was very easy to go to the market and so on, but it's not that easy, huh?
No. And also another thing to keep in mind is that when you go to the market, I mean, there are existing incumbent products there that use maybe other materials. So you have to make sure your new material makes better products. And also the incumbent material is evolving, right? You need to compare with the incumbent material of today, not of 10 years ago, because then the comparison is easier. But yeah.
And you develop several patents during these periods. Most of the patents are related to the sensors, to the fabrication.
A bit on the graphene material. So we have also patents related to the graphene oxide fabrication, mixing of GO with polymers. Yeah, also with the CVD graphene growth, not so much, but maybe transfer. We have not patented so much in products because we are not going to commercialize the final product. Yeah. We have some patents also on the devices, yeah, on the design of devices and so on, yeah.
No question, but I think it will come here, yeah. I think it's better. Just for the microphone, yeah.
Hi, Amaya. Thank you.
Hello.
Can you hear me? Yeah.
Yes.
So I have a question about the scaling up of the functionalization process, because you comment that it's really important not only at fabrication level, but also about the incorporation of these molecules or bioreceptors. According to your experience, how do you visualize this interface between the CMOS industry and the bio industry? You think there will be like clean rooms working in the middle, or how do you think could be the?
Good question. I think that there will be collaboration, and these biosensors would be integrated into CMOS. Yeah, definitely. Yeah, I guess we will have to develop good encapsulation and microfluidics in order to, let's say, to keep the CMOS intact and not damage it. But they will live together, definitely, because I mean, the electronics, we don't need to invent electronics, right? So we just take established technology and then make the biosensor on top. So they will, they will be integrated together, definitely. And about the functionalization at wafer scale, well, I guess, yeah, you would have to do the test in very small chips because CMOS wafers are very expensive. So yeah, once you have everything right, you move to the scale up.
Questions? Thanks. Questions there? Any question there? No questions there. I have a last question about, let's say, how is the muscle of the Spanish industry in spin-offs related to nanotechnology? You say that it's difficult to surpass the 5 years. I do agree.
Yes.
We also have one graphene company in here that failed. How do you think is now in Spain related to the field of nanotechnology, the spin-offs that are alive?
So for example, there is also Avanzare that they do graphene flex and they are doing really well. I think they have now a new building under construction. Of course, they don't do only graphene, but they do other nanomaterials also. And yeah, they are doing pretty well. I think with this European funding maybe has enabled that an ecosystem of companies working in nanotechnology to at least to start, establish, and then of course survive. But yeah, the surviving part is more complicated. But to start and yeah, at the end, a percentage also survives. So I think yeah, I would say in Spain is also becoming very relevant in terms of graphene and other nanomaterials. Yeah.
I think, as you mentioned, the key is to survive, to have the products and to have also the projects at the same time, because the projects give you some money for paying human resources, but at the same time, investing money for research that you need to continue. So we have a question from Raul. Yeah. Raul, maybe.
I saw in the chat, right?
Yeah.
How are you doing? Hello, hi. I don't know if the camera is working. That doesn't matter. Just one question regarding with the previous one that Reyes mentioned. And remembering the map that you show us, what are your customers, mainly located in Europe and also in America, and only few in Asia, in China. So what is your opinion regarding, in the flagship was always the debate, no? Where are the Chinese? And concerning this bio detector sensors and so on, do you think that they are a step further and in terms of development and in terms of commercialization of the systems and so on?
That's a very good question. I mean, China is typically the big unknown, right? Especially from the business perspective. I mean, we try to sell our materials in China, but we have not been so successful. It's difficult to know what they do. Yeah, I mean, they have a very good institutes that they do great research in graphene and into the materials. But yeah, to know exactly in biosensors what they do, I mean, is very difficult. Most startups that we are working with yeah, are in the US or in Europe, yeah, or Japan. In Japan, we do work with different groups, but yeah, China is the big unknown, yeah. But they are there and they invest a lot in R&D. So from that sense, it makes total sense. They will develop also biosensors, yeah.
No, that is the question, yes, because I remember the discussions with Thomas Rice and so on, that always from there, as you say, they are working on really an important role, but we are not getting this information. We are not getting what are they. And so on. Okay, so in any case, thank you very much, Amaya. Nice presentation. Take care. Bye to everyone.
Bye.
Bye, Raul. Any question from the audience? No questions? So I think we can finish. So thank you very much for your presentation,
Yeah.
Maya. I think. And you are always welcome to Zaragoza, to university, and our institute, Raul and the people. So thank you for your presentation.
Thank
and
you.
time.
Bye.
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 Yeah.